Today we are going to learn about mastering cross-validation with Scikit-learn. We will focus on implementing and interpreting cross-validation techniques to enhance your model's reliability and performance.
Welcome to our exploration of mastering cross-validation using Scikit-learn. In this video, we'll delve into the fundamental purpose and importance of cross-validation in the context of machine learning. Cross-validation is a statistical method used to estimate the skill of machine learning models. It is crucial for assessing the generalizability of your model to new data. By repeatedly training and testing your model on different subsets of your data, cross-validation helps ensure that your model performs well on unseen data, thus avoiding overfitting. Cross-validation provides a more robust estimate of your model's performance compared to a single train/test split. Scikit-learn, a powerful Python library for machine learning, offers a variety of cross-validation techniques, making it an essential tool for practitioners. Throughout this video, we will explore these techniques, focusing on their implementation and interpretation, to help you improve your model's reliability and performance. In the realm of machine learning, one of the most pivotal goals is to build models that not only perform well on training data but also generalize effectively to unseen data. This is where cross-validation comes into play. The primary purpose of cross-validation is to provide a rigorous assessment of your model's performance and to minimize the risk of overfitting. Overfitting occurs when a model learns the noise in the training data rather than the underlying pattern, resulting in poor performance on new data. Cross-validation mitigates this by splitting the dataset into multiple subsets or folds. The model is trained on a subset and tested on the remaining data, and this process is repeated several times. This ensures that every observation in the dataset has a chance to be used in both training and validation, providing a comprehensive evaluation of the model's ability to generalize. By employing cross-validation, you can make informed decisions about model selection, hyperparameter tuning, and feature engineering. It enables you to validate your model choices and ensures that the performance metrics you report are reliable and indicative of real-world application.
K-fold cross-validation is one of the most common techniques used to evaluate the performance of a machine learning model. The K in K-fold refers to the number of groups that a given data sample is to be split into. The dataset is divided into K equally sized folds. In each iteration, one fold is held out as the test set, and the remaining K1 folds are used for training. This process is repeated K times, with each fold getting a chance to be the test set. The performance metric, such as accuracy or F1 score, is computed for each of these iterations, and the final result is the average of these K values. This averaged result provides a more stable and less biased estimate of model performance than a single trained test split. K-fold cross-validation is particularly useful for small datasets where a single trained test split could lead to high variance in the performance estimate. It balances the trade-off between bias and variance by ensuring that every data point has a chance to be validated against. This technique is widely used and forms the backbone of many machine learning validation strategies. Leave one out cross-validation. LUIC is an extreme version of K-fold cross-validation where K is equal to the number of observations in the dataset. In LUIC, the model is trained on all data points except one, which is used as the test set. This process is repeated for each data point, providing a unique perspective on model performance. The main advantage of LUIC is that it maximizes the training dataset, using almost all data for training and only one point for testing. This can be particularly beneficial for very small datasets. However, this technique has significant drawbacks. Its high computational cost can be prohibitive, especially for large datasets, as the model needs to be trained as many times as there are data points. Additionally, LUIC can lead to high variance in the performance estimate, as the test set size is just one, making the model sensitive to individual data points. Despite these challenges, LUIC can be useful when the dataset is small, and the computational resources are sufficient. It's essential to weigh the pros and cons before choosing LUIC as your cross-validation strategy. Stratified K-fold cross-validation is an extension of K-fold cross-validation that is particularly useful for classification tasks, especially when dealing with imbalanced datasets. The main idea behind stratification is to ensure that each fold is a good representative of the whole dataset, maintaining the same proportion of classes as the original dataset. This is crucial for imbalanced datasets where certain classes may be underrepresented. By using stratified sampling, we can reduce the variance in the performance estimate and obtain more reliable results. In Scikit-learn, implementing stratified K-folds is straightforward, and it can be applied using the stratified fold class. This approach is not only beneficial for achieving balanced folds but also for improving the model's generalization capability by ensuring that each fold is as representative as possible. Stratified K-fold cross-validation is a robust technique that should be considered whenever dealing with classification problems, ensuring that the validation process is both fair and informative. Implementing cross-validation in Scikit-learn is both simple and effective, thanks to its comprehensive set of tools and functions designed for model evaluation. The cross_val_score function is at the core of Scikit-learn's cross-validation capabilities. It allows you to evaluate a model using K-fold cross-validation with just a few lines of code. You can specify the number of folds, the scoring metric, and even pass in custom cross-validation strategies such as stratified k-folds. Furthermore, Scikit-learn's cross-validation tools seamlessly integrate with its pipelines, allowing you to evaluate complex workflows that include data pre-processing and model training in a single step. The library also provides cross-validation generators that offer more control over the splitting process, including options for shuffling and stratification. Whether you're working with regression, classification, or clustering algorithms, Scikit-learn's cross-validation functions provide a robust framework for model evaluation, helping you to ensure that your models are both accurate and generalizable. After implementing cross-validation, the next step is to analyze the results to gain insights into your model's performance. The primary metrics to look at are the mean and variance of the scores obtained from the cross-validation process. A high mean score with low variance indicates a model that generalizes well to unseen data. Conversely, a high variance may suggest that the model is sensitive to the training data, potentially leading to overfitting. It's important to compare the results of different models and configurations to identify the best performing model. Visual tools like box plots can be extremely helpful in understanding the distribution of cross-validation scores, providing a graphical representation of the mean, variance, and potential outliers in the data. It's also crucial to be aware of the limitations of cross-validation. While it provides a robust estimate of model performance, it may not always capture all the nuances of your data, especially if there are underlying patterns not accounted for by the cross-validation strategy. Analyzing cross-validation results is a critical step in the model development process, helping you to make informed decisions about model selection and improvement.
While cross-validation is a powerful tool for model evaluation, there are several common pitfalls that you should be aware of to avoid compromising your results. One of the most critical issues is data leakage, which occurs when information from the test set inadvertently influences the training process, leading to overly optimistic performance estimates. To prevent data leakage, ensure that all data pre-processing steps are applied within the cross-validation loop. Another common pitfall is failing to properly stratify your data, especially in classification tasks with imbalanced classes. Without stratification, your folds may not represent the underlying distribution of classes, leading to biased results. Overfitting is another concern, particularly with complex models or when using techniques like leave one out cross-validation. It's important to monitor the variance of your cross-validation scores and consider simpler models or regularization techniques if overfitting is detected. Additionally, consider the computational cost associated with cross-validation, as some strategies can be resource-intensive. Finally, always validate the assumptions behind your cross-validation strategy and ensure that it aligns with your specific data and modeling goals. By being mindful of these pitfalls, you can ensure that your cross-validation process is both reliable and informative.
To bring all these concepts together, let's walk through a practical example of implementing cross-validation using Scikit-learn. We'll use a real-world dataset to demonstrate the process step by step. First, we'll load the dataset and perform any necessary pre-processing, such as handling missing values or scaling features. Then, we'll define our model and choose a cross-validation strategy, such as k-fold or stratified k-fold, depending on the nature of the dataset. Using Scikit-learn's cross_val_score function, we'll compute the cross-validation scores, specifying the number of folds and the scoring metric. Once we have the results, we'll analyze the mean and variance of the scores to assess the model's performance and generalization capability. We'll also explore different models or hyperparameters to see how they affect the cross-validation results. Throughout this process, we'll leverage Scikit-learn's tools to ensure that our cross-validation implementation is efficient and effective. This practical example will provide you with the skills and confidence to apply cross-validation techniques to your own machine learning projects, enhancing model reliability and performance. In conclusion, mastering cross-validation with Scikit-learn is an essential skill for any data scientist or machine learning practitioner. By understanding the purpose and importance of cross-validation, exploring different techniques such as k-fold and leave one out, and learning how to implement and analyze results using Scikit-learn, you are well equipped to evaluate and enhance your model's performance. Remember to be mindful of common pitfalls, such as data leakage and overfitting, and to choose the appropriate cross-validation strategy for your specific dataset and modeling goals. With these skills, you can confidently apply cross-validation to improve model reliability and performance in your real-world projects.